In our study of elimination reactions, we've seen how we can form alkenes by deprotonating our alkyl halide and shifting those electrons from our carbon-hydrogen bond in to form our new double bond. In our resulting alkene structure then, we have an area of high electron density. So if we look closer at our double bond here, of course we'd have our two carbons, each with their sp2 hybridized orbitals bonded together. So we'd have two electrons bonding here between our two carbons, and then we'd also have our two p orbitals overlapping above that in our pi bond, each with their two electrons forming that second bond as well. So with these two bonds here, we have an area of relatively high electron density, which we can use to actually reverse our elimination reaction and have an addition reaction. So we're going to take our electrons, which are going to act as essentially a nucleophile with our high electron density alkene, and we want to actually push this reaction backwards to reform our alkyl halides or our alcohols that we use for our elimination reactions. So we're actually reversing our elimination in this process of addition. So let's take a look at what these addition reactions will actually look like. So we're always going to start with our alkene double bond. So here's our alkene. We have, of course, our nucleophile here, our site of high electron density. And now what we're going to do is we can react it with a variety of different compounds, and we're going to add it to either side of that double bond. Right? So if we add H2O, water, this would be our hydration reaction, the opposite of our dehydration, and would give us an alcohol. If we add a hydrogen halide, HBr, or we could add HCl, we're essentially reversing our elimination reaction from an alkyl halide, and we are then producing our alkyl halide. We can also add other groups to our alkene double bond as well. So we can add hydrogen, this would be a hydrogenation reaction, and this would actually produce an alkane. We can also add halogen as well. So we can add two bromines, and we would then get an alkyl halide with each of those bromine groups adding on to our alkene double bond. And we'll look at other examples as well later on as we continue to look at our addition reactions. So in all of these cases, we're going to be taking one component of our reaction mixture. So let's say we add that H2O. So we're going to have, we'll lose our double bond. And we're going to add half of our molecule on either side of our previous double bond, right? So the OH from our H2O added to one carbon, and the hydrogen from our H2O added to the other. So let's take a look at the mechanism of this addition reaction. So we have our water here in our hydration reaction. Again, we're going to use our alkene double bond as our nucleophile. And normally, instead of just using water, we're going to use an acid catalyst. So if we modify this to our hydronium ion, now we have something that's relatively electrophilic. Right? So we have a positive charge. We have something that's electrophilic. It's acidic. It wants to get rid of that proton, and so that it can get back its neutral charge, take back its electrons. So we're going to take our electrons here from our alkene double bond with its excess electrons, and we're going to actually protonate our alkene bond in order to give our extra electrons back to that water. So now we would get our structure here. So we protonated our double bond, and of course this leads to the formation of a carbocation. Right? So only one of our carbons was able to form that new bond to a hydrogen. The other carbon lost out. It lost the electrons from that double bond, but it didn't gain any new electrons in our reaction. Right? So this guy is electron deficient. He's now a carbocation. On the other hand, our hydronium ion has become our neutral water molecule. So this water is quite happy now. It has its extra share of electrons with a partial negative charge, while our hydrogens would have their partial positive charges. And now with that partial negative charge, our water here can attack our carbocation. Right? So now we've kind of switched places where our carbocation is now more electrophilic, and our oxygen here is more of our nucleophile, and we can attack and create our alkyloxonium ion. So now at this point we just have to bring in another unit of water, and if we deprotonate our alkyloxonium ion, we form an alcohol. And again, overall, we added H2O, we added water to our alkene, and we lost our double bond right here. So we no longer have our double bond there between our two carbons, and instead we have our addition of that H2O. Of course, at the same time, we also reform our hydronium ion. This shows us that our acid here, our hydronium ion, just acts as a catalyst. Right? So this is our catalyst. It starts at the beginning of the reaction, and then it's reformed at the end of the reaction. So a catalyst is not consumed during our reaction. Now, of course, I should mention here, so our carbocation in this case is very unstable, right? So this reaction as drawn is actually unlikely to happen. Instead, we would want to react with a more substituted alkene, where we would get a more stable carbocation. So if we take a more substituted alkene instead for our hydration reaction, here we'll be able to form a more stable carbocation. Again, our alkene is going to attack. We deprotonate our hydronium ion, and we're going to get our carbocation product. Now you might notice, so again, these electrons from my double bond are attacking, but currently those electrons are between my two carbons. So there's an important question that we have to ask here. Which carbon is actually going to get the new bond to our hydrogen? And it turns out either of our carbons could take that new bond, right? So we actually have two possibilities here. We have one possibility where my carbon on the right takes the hydrogen. That would mean that my carbon on the left is now going to be lacking in electrons and will become that carbocation. I have another possibility where the carbon on the left takes the hydrogen. So we add our extra hydrogen here. We would of course have another hydrogen as well that's hidden in my normal bond line formula. And we end up with our positive charge on our other carbon over here. Now as we look at these two structures, we can immediately see that in the case up here we have a secondary carbocation, right? So we have our carbon here, and we have two carbon-carbon bonds from our carbocation. Our carbon down here is a tertiary carbocation, right? We have three different bonds to carbons from that carbocation. As we've learned previously, a tertiary carbocation is more stable because it has those extra carbons that can donate electron density into our electron-deficient carbocation. So since this carbocation is more stable, this carbon will tend to take the positive charge, and this carbon will take that hydrogen. So we're not just going to randomly pick which carbon gets the hydrogen, we're actually going to pick it according to our more stable carbocation. And of course, if we look at our other carbocation up here, you should notice that this carbocation would actually want to rearrange through a hydride shift in order to produce this more stable carbocation anyways. So if we go from this carbocation, our water, of course, would then attack. That would give us our alkyl-oxonium ion. Another unit of water comes in and deprotonates us. And we get our final alcohol. So again, we have our hydrogen that got added on one side. So we have one new hydrogen here. We have two hydrogens overall, compared to initially we would only have one hydrogen at this site to fulfill our four carbon bonds overall. And we have our new alcohol down here. So if we look at our final structure, our OH group got added to the more substituted carbon, right? That's this carbon here, or here in our original molecule. And our hydrogen got added to the less substituted carbon. This is what we call Markovnikov's rule. So Markovnikov's rule says that we're going to react with our alkene such that the more stable carbocation forms, and therefore so that our OH group gets added to the more substituted carbon. So, or in other words, our hydrogen is added to the less substituted carbon. So hydrogen adds to the less substituted carbon in our alkene. And this is a very important rule that we'll see repeated over and over again with our addition reactions. Right? So because we go through this carbocation intermediate, we always want to add that hydrogen such that we create our more stable carbocation intermediate here. This same Markovnikov's rule will apply for some of our other addition reactions as well. So if we add a hydrogen halide, so I'm going to use HBr here, but again we could use any of our different hydrogen halides in theory. So this is going to be the reverse of our elimination reaction from an alkyl halide. If we take our hydrogen halide, so our hydrogen halide again is a strong acid. So this is similar to the hydronium ion that we use to start our hydration reaction. Again, our double bond has those extra electrons. It can donate them to our acid. On our halide, from our hydrogen halide acid, we'll take those extra electrons to become our halide ion. Right, so we're going to get our free halide ion, our bromide negative ion in this case, and of course we're also adding that hydrogen onto our alkene. Now again, if we follow Markovnikov's rule, so we would have one possible carbocation if we added the hydrogen over here, This would be our secondary and less stable carbocation. And so our preferred carbocation would be if we added that hydrogen to the last substituted carbon, following our Markovnikov's rule over there. So we end up with our carbocation on the right and our new hydrogen added here on the left side. So our initial step looks just the same as it does for our alcohol-based hydration reaction. It's just that now our acid is actually our hydrogen halide. Right? So the hydrogen halide is a strong acid that can protonate our alkene and form this carbocation. At this point, again, our reaction will proceed as we saw before, except now we have our bromide ion to act as a nucleophile instead of water in the case of our hydration reaction. So if we attack there, we end up with our halide adding on at the more substitute position, and we have our hydrogen at that less substitute position. Again, following Markovnikov's rule. Again, we took our initial structure and we added the HBr from our hydrogen halide in this addition reaction. So overall, the reaction looks quite similar to our hydration reaction. It's just that we're adding a hydrogen and a halogen instead of adding our H2O from that water. Now, of course, one key difference that we do have here is that the structure of our hydrogen halide now is going to be a bit important for our reaction overall. So if we compare our different hydrogen halides, so of course we would have HF at the top, HCl, HBr, and HI. All our common hydrogen halides as we move from the top to the bottom of the periodic table. If we compare these different hydrogen halides, so our least reactive is going to be our hydrogen fluoride, and our most reactive is going to be our hydrogen iodide. This reactivity corresponds directly with our acidity, right? The stronger our acid is, the easier it will be for it to protonate our alkene, right? So this correlates directly with our acidity, where again our hydrogen iodide is the strongest acid because it has that weak bond to our hydrogen, right? So it can easily donate that hydrogen. It donates it to our alkene to form our carbocation, and then you'd have the great nucleophile of our iodide ion attacking to form our addition product of the alkyl halide. Besides the structure of our hydrogen halide, our addition reaction will also be strongly affected by the structure of our alkene itself. Right? So as we looked at our previous alkene here, we saw that when it reacted, it would form this tertiary carbocation that was relatively stable, right? And so we preferred to add our hydrogen over here so that we would have that more stable carbocation. If we have a slightly different alkene, so let's draw out this alkene here. So we replaced our methyl group here with a hydrogen, right? So in this case now, if we protonate this alkene, so let's say we add our hydrogen halide, it's going to add a hydrogen. In this case, both sides of our alkene have the same substitution, so it doesn't matter which side we add the hydrogen to. So we'll add our hydrogen there. This guy gets our carbocation. Notice here, of course, we only have two carbon-carbon bonds, so we have a secondary carbocation. And if we rearrange this and added the hydrogen to the right side instead, we would still end up with a secondary carbocation in either case. If we have an even smaller alkene, so just our 2 carbon alkene. So this is the alkene that I showed in my initial example. So here now we only have we have two identical spots to put that hydrogen. After we protonate this, in either case we would have this as our carbocation. Here's our new hydrogen. Here's all our existing hydrogens, and we would end up with a primary carbocation. Of course, as we know, that primary carbocation is less stable than our secondary, which is less stable than our tertiary carbocation. So this will also affect our reaction rates, right? If we're tri-substituted or tetra-substituted, we'll be able to form a tertiary carbocation, which is much more stable. So our reaction rate will be fastest for our more substituted alkenes that can form our tertiary carbocations. If we have a monosubstituted alkene that forms a secondary carbocation, that will have a moderate reaction rate. And if we have a unsubstituted alkene that forms a primary carbocation, here we would get our slowest reaction rates, right? Because we're forming that highly unstable carbocation, we're going to be much less likely to react. So this gives us a nice intro into our different kinds of addition reactions. So again, we're always adding those components on either side of our existing double bond. So one carbon gets one component, so we have our hydrogen shown here in pink, and then we would be adding our other component to the other side. So this would be our halide, or it could be our alcohol if we're doing our hydration reaction. So we'd end up with our alcohol here. In either case, we're following Markovnikov's rule, where that hydrogen is going to the left substituted carbon to allow us to form that more stable carbocation, and our other group, the OH group or the halide, is going to the more substituted carbon, which will initially get our carbocation. Now, as we'll see, this rule doesn't apply for all of our addition reactions. So as we get into some of our other addition reactions, we'll see how they can actually manipulate this reaction so that we don't follow that standard Markovnikov's rule.